Hello grade 11, Mr. G here, and we are going to make a video related to Newton's law of universal gravitation. This is a video, a question to practice, okay? It was in a previous question paper, and let's go for it. The question say, Zakube 1, the first South African satellite, was designed and built by postgraduate students following the CubeSat program and the French South Africa Institute of Technology, in collaboration with the South African National Space Agency. Zakube 1 was launched on the 21st of November 2013 and is orbiting at a height of 600 kilometers from the surface of the Earth. That is important. It's very important data. So let's just highlight it here. Okay? Weighing 1.2 kilograms, that is Zakube. The CubeSat is about 100 times smaller than Sputnik. 100 times smaller than Sputnik. The first satellite launched into space in 1957. 1.1 states Newton's law of universal gravitation in words. Okay, so let's go down here. There is the answer. The question the law states that each particle in the universe attracts each other with a gravitational force. This is a force, is the name of the force. In previous video, we saw that one of the questions was the name of this specific force. So the name is gravitational force. Now this force is directly proportional to the product of their masses, right? And inversely proportional to the square of the distance, between the centers. So this is the law. And this law, when you have exam, it will carry 2 marks. One for saying that force is directly proportional to the product of their masses, and it is inversely proportional to the square of the distance between their centers. All right? So that is the law, and then you have 2 marks for that. All right, now let's quickly, before we go to the next question, recall this could be written in a formula way. So the formula for this law is this gravitational force is equal to G multiplied by the product of the mass of the first object, mass of the second object, divided by the distance between those 2 objects square. All right, now this, in the relationship, we can say that the gravitational force is directly proportional to the product of the masses of the object and inversely proportional to the square of the distance. This is the law, but it's in symbols. They ask to write it in words. Okay, so that is the first important thing here. But I want to also mention, before we carry on, because it's going to be just mentioned just now, this is the distance between the center of the 2 objects. For instance, let's say we have 2 objects. Here we have 2 objects. That distance we're speaking about is the distance between the center of one object to the center of the other object. So this is that R or D. It doesn't. The symbol is not really that important. That is the distance we're speaking about. It's the distance between the center of one object to the center of the other object. So it's not from the surface. It's not from here to here. Is from the center of the object. That is the distance we're speaking about. So I hope that is clear. All right, so let's go to the next question. This is regarding the law. The next question says, how would the magnitude of the gravitational force exerted by the Earth on Zakube 1 compare with the magnitude of the gravitational force exerted by the Earth on Sputnik if both satellites were orbiting at the same height? Write larger than, smaller than, or the same, and explain your answer. So for that question here, we make a small picture to understand what is going on. All right, so here we have the picture is the Earth, the Zakube, and Sputnik. Now what is important? The distance is the same. They say the distance is the same. However, previously they told you that the mass of Sputnik is 100 times bigger than the mass of Zakube. That is important. The mass of Sputnik is 100 times bigger than the mass of Zakube. So if we have that the gravitational force is equal to the constant multiplied by one object, the other object, divided by the distance square. This is the formula, okay? Now let's do a small, very, very small analysis here. I don't want to make the video too long. But here, in this case, this will be the force of gravity between Sputnik and Earth. I'm going to write S and E. It's G, which is constant, the product of the mass of the Earth multiplied by the mass of Sputnik divided by the distance between the Earth and Sputnik square. And for the Zakube, we have that the gravitational force on the Earth's own Zakube, remember it does not really matter which one we write first, is equal to the constant multiplied by the mass of the Earth, mass of Zakube divided by the distance between the Earth, the center of the Earth, and the center of Zakube square. If we look here, we can see the following. The distance is the same. They are at the same height from the Earth. The mass of the Earth is common. Alright? And G is constant, so it's also common. So, what can you see? The one that have a greater mass of the second object will have a greater gravitational attraction. In this case, will be Sputnik. Sputnik, the mass of Sputnik, they say that the mass of Sputnik is equal to 100 times the mass of Zakube. So, the gravitational force of attraction of Zakube is 100 times smaller than the gravitational force from the Earth on Sputnik. This one is the answer. It's smaller than. The question is, how is the force on Zakube compared to the force on Sputnik? So it's smaller. In fact, it's 100 times smaller. It's 100 times smaller. And the explanation you can see there between the drawing and some formulas, and you see what is common, etc. Okay. So let's go to question 1.2. Let's go to question 1.2 real quick. Question 1.3. Calculate the gravitational force exerted by the Earth on satellite Zakube 1. Here, I already separate the data. This is no. However, I want you to note the following. Here, you can see that the mass of the Earth is not given, but it's a data that is in the table of constant. You need it, and the radius of the Earth you need it as well. All right, why? In the previous drawing, we're going to make a very quick drawing here. It's not the same. Here is the Earth, and the satellite, let's say, is somewhere there. This is Zakube 1. Now, they are giving you the distance from Zakube to the Earth. They're giving you the distance from Zakube to the surface of the Earth up until there. And they say that distance, I wrote D, is equal to 600 kilometers. Alright? Now, remember, you cannot work in kilometers, so that is why we did convert times 10 to the 3 or times 1000, okay? So it's the same. That is the distance. However, as we explained here, and that was the purpose, it must be from the center of one object to the center of the other. Zakube is very small, so the center of Zakube does not make any change, but the Earth is big. So here we need the radius of the Earth, because the total distance, this is the radius of the Earth. The total distance from Zakube to the center of the Earth will be the addition of the radius of the Earth plus the distance of 600. So let's say if we write here the distance we are going to use between the Earth and Zakube is equal to the 600 kilometers plus the 6,378 kilometers of the radius of the Earth. Alright, and the answer here will be 6,978 kilometers. This is the total distance from center of the Earth to Zakube. This is the distance we have to use in our formula. Alright, remember, we have to convert into meters, so it will be equal to 6,978 times 10 to the 3 or times 1000, and that will be converted to meters. Okay, so now the rest is just to write the formula and the substitution. Okay, so here is the gravitational force is equal to G mass of the cube, mass of the Earth, divided by the distance between the cube and the Earth, which remember we did calculate it here at the bottom. Okay, so here if we substitute now, we have that G is equal to 6,67 times 10 to the minus 11 times the mass of the cube is it is on top 1,2 times the mass of the Earth is 6 times 10 to the 24 kilograms, everything divided by the distance, which we did calculate there, so it's 6,978 times 10 to the 3 and everything to the power 2. So the gravitational force, this attraction between the cube and the Earth, is going to be equal to, the answer is 9,86 Newton. Now let's quickly go to the equation. They said calculate the gravitational force exerted by the Earth on the satellite. So if we come here, the direction, the force is being acting from the Earth on the cube. So the force is going to be towards, you can see here, is towards, this is the force of gravity from the Earth on the cube. I hope you can see it here, and it's towards the center of the Earth. So it does have direction, and the direction is toward the center, towards the center, you can write towards the Earth. This is the final answer for this question. So let's give marks, because this is to practice. You will get 1 mark for the formula. You are going to get 1 substitution for the denominator, 1 mark for the denominator, 1 for the final answer, and 1 for the direction. But it's not always going to be like that. So this question is 5 marks. And we're going to the last one, which is a little bit tricky. This question said, calculate the height the satellite must be orbiting for the value of the acceleration due to gravity to be 25% of the gravitational acceleration on the surface of the Earth. So this question, they say that calculate the height. Let's go back. The question is quite tricky. Calculate the height of the satellite must be orbiting for the value of the acceleration due to gravity to be 25 degrees of the acceleration, gravitational acceleration on the surface. So the question is a little bit tricky. Here is more or less, this is the Earth, right? This is the surface, the satellite is there on the surface, and that is more or less the radius of the Earth. Okay, now the satellite is going to be somewhere further away, and they want to know what is the distance now. Okay, this, let's say position 1, and this is going to be position 2. So they want to know what is the height from the satellite, how far is the satellite, okay, from the surface of the Earth. They say height. Okay, so that is what they want. This is height, and we're going to be working with height. Now, what do we know here? We know that the satellite will have certain acceleration here at the surface of the Earth. I'm going to call it 1. This is at surface. And we are not going to write 9,8 because we don't know if it's 9,8. So they didn't say that we have to use 9,8. They say that it's going to be at certain point, and the acceleration here is going to be 25%, sorry, not 20, 25% of the acceleration due to gravity of G1. So this G2 is going to be equal to 1/4, 25 represent 1/4 of G1. I hope this is clear. It's a little bit confusing, all right? They are telling you that the acceleration due to gravity, they say that the acceleration due to gravity at that specific point there is going to be 1/4 of the acceleration due to gravity right on the surface. Okay, so that is the important, the very, very important work here. So we have 2 points. We have at surface, and we have at point 2. So we're going to call at surface point 1, and red there by above the surface, we're going to call point 2. So at surface, we know that we can calculate the acceleration due to gravity using the acceleration that is here. So we're going to say acceleration due to gravity is equal to the constant of gravitation multiplied by the mass of the Earth divided by the distance between the center of the Earth and the surface, which is going to be the radius of the Earth square. So this is at surface. We're going to call at surface 1. Okay, so here is at surface, and we're going to see at some point. All right. Now this one is at some point where the acceleration is equal to 25% of the acceleration due to gravity. Okay, that is 1/4. All right. So now then, the acceleration due to gravity there is also equal to the acceleration due to gravity 2 is equal to the constant multiplied by the mass of the Earth divided by the distance between the Earth and the satellite. But that distance is going to be the radius of the Earth here plus this h. That is the total distance that is going from the center of the Earth to the satellite at the second point. So all this one is the distance that we are talking about. Okay, so that distance here will be the radius of the Earth plus the height h, which is actually, in actual fact, what we're looking for. Everything divided to the power 2. Okay, so this is what we have up until now. All right, so here we are. At some point, we have this to calculate the acceleration due to gravity. Okay, now let's look at the following. This point here and this one here are the same. It's a constant and it's the mass of the Earth. So let's substitute to calculate that one. Okay, so here we will have the constant multiplied by the mass of the Earth is going to be equal to the product of the acceleration at the surface of the Earth multiplied by the radius of the Earth to the power 2. Okay, and here on the other side we will have that the product of the constant of gravitation multiplied by the mass of the Earth is equal to the product of the acceleration due to gravity at certain point where it is 25% of the acceleration at the surface of the Earth multiplied by the radius of the Earth plus the height at which the satellite is going to be allocated. All right, so we are here, and therefore, because those points are equal, we can equate now. All right, so let's equate, and we have that this is equal to this. So the acceleration due to gravity at the surface of the Earth multiplied by the radius of the Earth to the power 2 is equal to the acceleration due to gravity at certain point multiplied by the radius of the Earth plus certain height and everything to the power 2. Okay, so we have this one, but remember the acceleration at certain height is going to be 1/4 of the acceleration of the surface. So that is what we are going to substitute here. Okay, so we have that the product of the acceleration due to gravity at the surface of the Earth multiplied by the radius of the Earth to the power 2 is going to be equal to 1/4, and not 2, not half, 1/4 of the acceleration due to gravity at the surface of the Earth. Okay, multiplied everything by the radius of the Earth plus the height at which the satellite is going to be allocated. Okay, so we are here. If we work and we move this 4 to the other side, we have that 4 and not 2. I would like to do once more. I'm very sorry. It's 4 multiplied by the acceleration due to gravity at the surface of the Earth multiplied by the radius of the Earth to the power 2, and then on the other side we have that the acceleration due to gravity multiplied by the radius of the Earth plus the height, everything to the power 2. Okay, so If we move now the acceleration due to gravity to one side, we have that 4 multiplied by g1 multiplied by the radius of the earth to the power 2 divided by the acceleration due to gravity, I move it to the other side, is equal to the radius of the earth plus the height of, at which the satellite is allocated to the power 2. And this is gone. They simplify each other. So what do we have now? We have 4 multiplied by the radius of the earth to the power 2 is equal to, and we can solve this one. This one is the square of the first plus the double, the second multiplied by the first, so it's 2hre plus the second to the power 2. That is h to the power 2. Okay, the other way you can do, if you don't remember how to do that one, you can say re plus h multiplied by re plus h. And remember, you have to multiply this times each of them and this times each of them. And then you will get this one as the solution, okay? After you do that product, all right? But you can do it later. You can go to your maths teacher if you don't understand how to solve this one. It is very important because in mathematics you are going to use it many times, all right? You can use other letters like x and y or z and w, whatever letter is more comfortable for you in mathematics. Okay, so if we move this one, this square to the other side, or everything to the other side, we have that. Let's just fix that one quick. If we move all this one to the other side, we have that re square plus 2h re plus h square, and this one is going to the other side negative, minus 4 re square, everything is equal to 0. All right, here we have common factors. This is common factor with this one, so we can sort it out, and we will have, if we arrange as well, h to the power 2 plus 2h re minus 3re square is equal to 0. And we can factorize this one. We can factorize it right now. Also, you can always you make use of your maths teachers to help you how to factorize. Maybe they explain much better how to solve the factorization, okay? But I'll do it in my way. All right, so here you have to look for two numbers that can give you this one as the product, and that will be h and h. H times h is h to the power 2. And here you have to look for two numbers that when you multiply them, they'll give you this one here. And that one will be 3 re and 1 re. Now note, when you add those two in a cross product, they must be able to give you what you have here. So if we add 3 plus 1 is 4. So we are going to make one of them negative. However, you can see it must be the highest one, the bigger one must be positive. So this one is minus 1. 3 minus 1 is 2. So the factorization here is going to be h plus 3h minus r3. All right? So what do we have? We have h plus 3 re, and we have, this is equal to 0, and we have h minus re is equal to 0. Okay, this one is a re. Note here, it's a either. All right, so here h will be equal to minus 3 re. That is wrong because we have a negative answer there. And here h is equal to re. So what does it mean? This is the radius of the earth, remember, that is the radius of the earth. So what does it mean? That this distance in the picture, this distance here is going to be equal to re. All right, the question is, let's go back to the question, calculate the height of the satellite, and the height of the satellite then must be equal to re. So h is equal to re, which is equal to, we go into the previous question, the data, the radius of the Earth is 6,378 times 10 to the times 10 to the 3 meters. Times to the 3 meters. That is the height at which the satellite is located. Okay, so that is the answer. I hope it's well understand. This specific question is difficult. It is a lot of work, but I did my best to make it simple for you. Thank you very much. Good luck, and I'll see you next time.